And then a bit different topic, so this one is more technical. So that one was text-related stuff. So the linguist part of people worked more. Here it's more technical stuff, and it's, well, indirectly medicine-related. So it's the respiratory motion compensation in radiotherapy. So I already told a bit about this project, but I think that's one of the most interesting projects we did, actually. And when you work on medical projects, if things work well and they decide to use it, or at least they put it into their plans to use it, and you know that it can help people, it always feels better than just doing very generic project. So the idea is that when you have radiotherapy in lungs area, actually your body moves quite a lot. And while you want, if you have radiation therapy, it means that your condition is not good already. And in addition, if you want to irradiate, especially smaller tumors, of course you want to irradiate only tumor. You don't want to attack healthy tissues as well. And when you breathe, actually your body can move quite a lot. So in our case, it was up to 3 centimeters, I think, with our patient base. But actually, if you look at literature, so probably some big people, it could be like 6 centimeters, or even, I think I saw in some paper 9 centimeters. So it means that person has big lungs, maybe big body, and it really goes up and down. And then, of course, there is another thing. So basically, when you lay on the couch, body sags down slowly. So it means that position of your body changes over the fraction as well all the time. So we decided to cooperate with company Radiotherapy on this project, and the idea was basically simple. So we were building these, or we used couches built by some Austrian company, but we write software to position patient in very exact position. We use stereo cameras to look at the position of the couch, and here you can see some markers which we put. So here it's on this part, but you can put these markers on the body, so they are very well visible. And with this camera, you can track them precisely, and it can be done in almost real time. And this actually couch, it's robotic couch, so it's so-called hexapod robot, so it can change position in all the directions, so it's in different axes. So actually we can position patient very precisely. And the idea was to make the couch move during traction, that basically you follow how patient breathes, and when you move maybe up and down, maybe a bit different positions as well. So in the end, for us, it was just up and down. And actually what is done, so of course people know the problem and they do different things. So of course it's still quite common that you don't do anything. You just irradiate, you burn tissue around this functional target, and that's all. Then what we do gating. Gating, the idea is very simple. So basically you calculate position when your tumor is in specific area, when it moves. And when it moves like that, basically you switch device when it's here, and when it goes up and down, you switch it off. So basically you switch this linear accelerator on and off all the time. Then what you do as well, so some doctors, they try to train patients. So basically they control their breath. So they breathe slowly. But usually it's a big issue, because if it's old person, if they are in bad condition, it's almost impossible for them to do these things. Then you can do some probability-based planning. So basically you look at the volume of the tumor and you plan it in such way that maybe you change strength of the signal and try still to irradiate
good tissue less and bad tissue more. Then actually what you can do, you have this so-called Mutilative Collimator. So it means that you have some small leaves like in old cameras where you can open or close them for radiation. So you can change these things. You can change, in general, you can change configuration of linear accelerator. Or you can use this support structure, move the patient. And the idea was to use the last thing because we were working on these things already. And actually at some moment we were thought that it could be issue because when you move people, maybe they can get seasickness, but that was not the case. And I mean, as scientists and engineers, of course, we did not go to radiotherapy, but we did these experiments ourselves. So when we had the software to control this device, we just tried, to lay on the device and see how it moves and how you feel as well. And actually, literature also shows that people don't have issues with this motion, so you don't get motion sickness. Well, the idea of doing these things, it sounds pretty trivial as well. So basically, you have to determine position of tumor, you have predict motion, and you have adapt the position. But when actually, it's not as trivial as it may sound, because predicting position of tumor, it's non-trivial thing. And actually, you have to do two things. First of all, you cannot see tumor inside the body during radiotherapy. So you can go to computer tomography or to magnetic tomography to collect the data, how your body moves. And this motion mostly is based on, of course, your birth pattern, but also the tissues in your body, how elastic they are, how big are your lungs, etc. And then actually during fraction, you can have only these external markers. You have to follow them, and based on external markers, you look at how they move, and based on their motion, you predict what's happening inside person's body. So we did experiments with a number of different models. So it was from something very basic like superposition of sinusoidals, Kalman filters, artificial neural networks, to number of actually, maybe simpler, but quite well-performing models such as regressions, ARM, wavelet-based multiscale autoregression, multi-step linear models, etc. And so just to show a bit more how it's happening, so actually you have these three directions in the body, and when you have these directions on the couch, you put them like that. So, and this one you already saw, so that's how motion looks like. And the motion, so some of the motion data we have collected from medical records. So they provided us with some CT scans, but they were very short. They were something like half a minute, because on computer tomography, you cannot keep patient for a long time because it's radiation as well. And then actually we had opportunity to use this magnetron device, so magnetic tomography. So actually me and some of my colleagues we spent like half an hour in this device to collect different data. It was not big fun because it's very noisy. And actually, if you are fat, it's very visible. So it means that people who record you, they make jokes on you for half an hour and you cannot really answer anything. So, but still it was very interesting. And then based on that, we also got additional data from some people in Germany who were working on these things, and a bit on the team who worked for a bit with different company in the US, the Varian company. But basically what we noticed actually that if you look at the motion, it's very different in different directions. So actually
in most of the cases, if you look, at direction along the body, motion is very low. It's almost neglectable. So it's less than, it's 2-3 millimeters at most. And usually, anyway, you have to irradiate a bit bigger area. You have to burn a bit of tissue around the tumor as well. Actually, if you look at the motion to the sides, it becomes important only if your target is only on the sides of the body. If it's on somewhere near top, it's less. But up and down, it could be really a lot. So here, for example, it's something like 25 millimeters, maybe even 30 millimeters. And that's just some signals, how it was actually, how it looked like. So of course you have discrete signals, it's quite dirty. And then we did some relations. So you have magnetron, you have something outside the body, some functional target. So of course that probably motion of things inside my body and outside my body as well. But basically, of course, we did not have tumors, so you just choose some very visible marker inside your body. So it could be some part of bone or some, well, so in magnetron you can see the tissue. Of course, when you have to irradiate people, of course, you look at tumors there. So on the left side, these are internal markers. So basically what you would have to, no, actually, this first, second, and third are markers outside the body. So it was, I think it was here, here, and here, different positions. For all the patients we made experiments with, you look how much they move. And then actually these from P3 to P9 are internal markers, so you look at different points in the body and see how much they move. And that's just, motion of these targets in different directions. So as you see, in some cases, some targets were moving up to 8 millimeters in specific cases. And when actually invent, so our best results we have achieved using so-called cold winter smoothing with modifications. And we did several modifications, and depending on the breath patterns of the humans. So basically, cold winters is a very simple model. So you say that you use the same prediction all the time, but then you look at seasonality. So it means, in sense, seasonality, of course, it comes if you would look how, for example, sales or temperature depend on a yearly period or on a weekly period. Here, of course, it's just breath going up and down. And then you can look at the trend, so is it going up and down, and then you just repeat the motion. So, and we looked at actually two measures of errors. So one is general error, so how far is your prediction from your functional target. But another thing which is actually quite important when you use devices is so-called jitter. So for example, if you have a line and you have to follow it, you can do it like this. It means that you get a high jitter, and if it's device, it means that it has to go up and down all the time. And actually, if it's physical device, it could be quite a big problem. Because it moves up, it has to stop it has to go down. And the motion could be like 3 millimeters. So we did not broke this couch, but it was making very strange noise when you had all this jitter all the time, like chattering. In some cases, it's called chattering as well. So we wanted to minimize this thing as well. And when we've got very different prediction results with different models. So ES2 and ES3 are these two cold winter models. ES2 is simpler model, ES3 is more complicated. It was best for performing model from the literature. And B1, B2, these were baseline models, so something very basic, like saying that, the position will be the same in the next step. Or the position will be like difference between last two steps.
And then, as you can see, you get very different results. So you can get very high jitter in some models, and in some models you get low jitter but big error, etc. And if you look at average performance, so for example, in Mullen, you get low error compared to baseline and comparable to others, but you get a lot of jitter. And actually, simple model and even baseline models, they have quite low error and quite low jitter. Lowest jitter, of course, you get in the model where basically you just follow the readings. So you remain in the same position. When you get reading, you follow. So basically you are late one step all the time. So it's low jitter, but of course it's big error. And that's just some example what happens. So true signal and how the green line shows how you can follow it. So with ES2, you can get bigger error, but then you have less jitter in that case. And some relations of markers. So basically, actually in the end, I don't have it in these slides, but we decided to do switching algorithm. So you start from using this ES3 model, so most complex model, but in parallel, you run all the models and you do calculations. And after certain amounts of steps, you calculate the error, and if you see that actually every model is doing better, then you switch to another model. Then again, you make several steps, you do calculations, and then actually if patient, let's say, patient's respiration, well, very good maybe is not right word, but very periodic, very clean, then ES3 is the best model. It follows very well, and you can do it well. Actually, if patient's breathing is more hectic, then you may switch probably, or at some moment it becomes more hectic, you can switch to ES2, or even to B2, which is just, you add average of, you follow it stepwise. And then actually, for some patients, in the beginning, when we lay on the couch, we are very afraid. So we really breathe very badly, and it means that you start from a worse model, but you have less jitter, and then patient becomes calm, and you can switch to better model and follow with it better. So basically, we have built working prototype. We did not do ourselves experiments in radiotherapy, so it was just the motion of the couch with, let's say, dummies or humans on top of it. And then actually what we have noticed that if you want to control using couch to prevent this, to compensate this respiratory motion, jitter is very important. Because if you have mechanical device with jitter, or in system in control, sometimes it's called chattering, it could be quite big issue. So you can break the device if you do it all the time. Also, we were very surprised ourselves, but artificial neural networks were very unstable. So in some cases, we were doing very well, but in some cases, it was complete disaster. So in the end, that's why they are not in the list. And as I said, we built a model where we use combination of different components. So that basically was our result. And that's another research topic which I wanted to discuss with you. So one was more textual stuff, this one is more technology related, and just a short look. So that's one of the projects. So we cooperate a bit with our financial crime people, not much, but just to present the idea. So there are quite a few, maybe you have heard about different offshore leagues.
databases, so Pandora, Panama, Bahamas box. And then actually, because we worked on credit scoring models, we had a lot of data about Lithuanian businesses as well. And we decided, to look actually what you can find there. And it was quite fun because we were able to identify some people related with big companies in Lithuania. So we just keep the name of the guy. We don't want to use last name. We don't want to have any issues with them, but that's the number of companies he owns in Lithuania. And then actually he has quite a few companies in offshore zones as well. And then, of course, you can look at the relations, so you can see, of course, it's more interesting for Lithuanians because sometimes we can find some names of some famous people in Lithuania which are related in some strange companies which are not clear, but we are doing on some politicians as well. And basically that's the, let's say, companies, so people who live in capital and in Kauntas, second biggest city, so usually so people from these cities has most offshore companies as well. And some networks, so again, we have removed all the names and companies even from the network here. But actually, if you look at the relations, how we make these joint companies, you can find a lot of interesting things. And basically what we used only open source data. So all these offshore leaks which you can download. And basically in Lithuania, you can get openly a lot of data about companies, so directors, their finances, so because we do yearly financing report, etc. So this one we have presented in several events, and actually, well, our financial crime people were very interested, but when we said that we don't want to buy anything for us, but if we want, they can hire us to work as police people, and we said, no, thank you, we prefer research. But it was fun, and it was part of some small hackathon, so it was like 3 days of work to build all these things. So I wouldn't call it real research, it's like pilot of research. But you can extract from different data using different tools, etc. Then that's some just snapshot of some research long time ago. So we looked at different alternative Lithuanian media. By alternative mean that basically the media where they strongly attack government and president. And basically the topics we discuss. And actually here you can see some left-wing people who are almost communist or who support Russia, for example, a lot, or right-wing people who are actually probably really are not just nationalists, but even worse. So all the spectrum. But when you see the topics which we discuss and relations, who cite whom, and actually in which channels they write, it seems that we are strongly related. So somehow, for us, it was surprising as well, because we had some political decisions. Should you do this fraction where you can extract this thing, which I don't remember how it's called in English. It's not oil. It's something similar to oil, but they do a bit of that in US. A bit in Estonia, I think, as well. But basically, it's a very dirty process. So you have to use so-called fracking, and you can pump it out from the ground, but then it's high risk that actually your underground water may get polluted. So actually, we were fighting against these things, and we were organizing some demonstration together, both left-wing and right-wing, but really extremes. Then we had some political discussion, can we sell land in Lithuania to foreigners or not, agriculture land? And again, general opinion, it was okay if we want, let them buy, they can, grow something, do something with that, and all these, both sides even if we are opposite, we are still there against that. Then there were more topics like, should we close nuclear station or shouldn't we? Should we build new one or shouldn't we? And it was surprising. So we are kind of fight each other, but when it comes to these discussions, we come together often. And some more research, so that's PhD students. She's PhD student in social science, and we looked at Facebook groups. Again, extreme Facebook groups, radical Facebook groups. And again, we found this strange thing where you have people who are pro-Russian, but they claim that they are Lithuanian nationalists in the same group. And we have, these pictures of Karl Marx like that, some strange things. But for example, they are against foreigners in Lithuania. So actually, we were happy to be able to do that research before Facebook closed access to the data. So nowadays, you wouldn't be able to download this data for analysis. But so Rasa did that. She's PhD student in ethnology or social scientist, but I was kind of technical consultant. So it was really interesting to see their discussions and how they behave. And it was kind of covert operation as well, because she just became a member of these groups. She didn't tell that actually that she's doing research, so we just collected discussions. We didn't look at specific names of people. We just collected discussions, to identify topics they discuss, etc. So I don't know why and how we have this strange thing in Lithuania that somehow extreme left and extreme right, quite often we are together, which is, okay, it's not computer science question, I think it's social science question, but still, we did these joint projects and it was very surprising. And these are just some topics, it's in Lithuanian, so hate speech, I already mentioned that. So basically, that's all I wanted to tell you today. So I gave a list of general projects we do, and then I just discussed some research projects we did as well. So if you have any questions, feel free to ask now.